Okay, so first thing, test, regarding the test, we're going to do this test on Thursday.
Can we push it one day?
What's that?
Can we push it one day? Like Tuesday?
Next Thursday? We can't do it next Thursday?
Is it not push it one more day? No? The Tuesday? One more weekend? I mean, if not,
All right.
it'd be good.
Is that what you guys want?
Yes.
Yeah.
Want to do it on next Tuesday instead?
Well,
Yeah.
on the 11th, it's not gonna, it's Veterans Day though.
Oh,
So
yeah.
there's gonna be no class anyway.
What day is Veterans
On
Day?
the Tuesday?
On a Tuesday.
No, it's class. We have class. We don't have holidays until
On Veterans Day?
Yeah.
Oh, that's the, oh yeah.
We don't have
Yeah,
that.
We
it's-
still have-
Yeah, we have class.
No, you don't.
No, we don't.
You sure?
That's
Oh,
the
no,
eleventh.
the 11th, no, there's no class.
So that was-
Somebody hasn't even said
It's
that.
Veterans Day. We don't have to do it. Because my instructor already told us that there's no class.
Yeah, so mine.
All right, we're having the test on Thursday. I can't put it off that long. But the good news is that, you know, we don't have that much left to cover. So we're gonna look at we looked at the Gibbs free energies of solids, liquids, and gases a little bit when we had single component systems, single components that contain the solid, liquid, and the gas state. We're going to just expand on that just a little bit and start looking at the Gibbs free energies of solutions today. And there's a little bit of not circular logic. There's some strange logic. I'll call it strange, and then you guys can decide how you feel about it. That allows us to quantify the Gibbs free energies of components in solution. So we're going to look at that on Tuesday of next week. We'll come in and I'll just touch up on phase diagrams just a little bit, and then we'll do a bit of a review like we did last time before the test. Okay, so there's going to be a review on Tuesday. I'll send you, I haven't gotten the homework for this chapter printed up yet, but I'll print up a homework and send out, and then we'll review that homework and other topics on Tuesday, then we'll come in on Thursday and take the exam. So that's the tentative schedule for next week. That is the schedule for next week. Okay? Now to what we're looking at. So that's not the slide I need. Hold on a second here. We looked at this expression last week. dG is VdP plus minus, SdT, and that was the expression that allowed us to plot the Gibbs free energies versus temperature and pressure for the single component systems, and to look at how changes in pressure and temperature changed the which phase was favored. We're gonna stop and look at this equation again, and we'll look at something we already looked at, but just state it one more time because it applies to the logic that we're going to do here on the board in a second. If temperature is constant, if there's no change in temperature, but pressure varies, then the change in the Gibbs free energy between, as you go from P1 to P2, is going to be the integral of VdP, right? And for the ideal gas, we had that the ideal gas was nRT, the volume of the ideal gas was nRT over P. So you can plug in that volume, you get the integral of nRT over P dP for delta G, the change in the Gibbs free energy. nR and T are constants, so those guys come out. And we're integrating 1 over P dP. And we get that expression that delta G is equal to nRT times the natural log of P final over P initial for a gas phase species. And we'll want to convert this into a molar Gibbs energy. All we have to do to convert it to a molar Gibbs energy is divide through by N. And so delta G over N is delta G M, with that little m there to signify that it's the molar Gibbs energy. And that's going to be RT times the natural log of P final over P initial. Right now, before we move forward, I want you guys to realize that this term here, delta GM, the molar Gibbs free energy, it's the Gibbs free energy per mole of species. It's also written as mu, the chemical potential. Right? So if you see this symbol, the mu symbol, know that that's just G of GM is just the equivalent to mu. It's the Gibbs free energy per mole of that particular species. We're going to be using the symbol mu a lot, so just know that mu and G are the same thing. So delta mu, delta G, same exact expression. So a couple of things to note. We end up with that same expression that we had last time, where the final value of the function was the initial value plus that correction. We know that our correction is nRT line P2 over P1, and if we convert to the molar energies that we get, GM of P2 is GM of P1 plus RT natural log of P2 over P1. You'll note that this term is positive if P2 is greater than P1, and it's negative if P2 is less than P1. And so something to be aware of is that suggests that as the pressure of the gas phase species goes up, its Gibbs energy increases. So the higher the pressure of the species, the higher the Gibbs free energy of that species. And conversely, if the pressure drops for an ideal gas species, the free energy of that species is dropping, it's decreasing. And so when any gas is at a high pressure, it's at a high free energy. And when it's at a low pressure, it's a low free energy. All right? We want to remember that for the rest of the conversation that we're about to have. What we end up doing is we define the reference state as being that 1 atmosphere pressure that a lot of reference states are defined at, or 1 bar pressure that reference states are defined at. And if you plug in that value of 1 bar for P1, then the expression simplifies, because anything divided by 1 is simply the value of that. And so this RT line P2 over P1 just becomes an RT natural log of P, right? If we decide that P naught is the P of the reference state, and that that's always 1 bar, then this is always 1 in the denominator, and so our expression for the chemical potential ends up being the chemical potential at state 2 is the chemical potential at the reference state, which is 1 bar, plus RT natural log of whatever the new pressure is. Yeah? And so oftentimes you'll see something that just is cast in terms of that pressure, but you always have to remember that it's already been divided by the reference pressure of 1 bar. Okay? So, we're going to try to apply this real quickly to a problem. And the problem that we're going to look at is the mixing of ideal gases. So, say we have 2 containers. This example is taken right out of your text, so you can go back to the text and take a second look at it if you need to. You take 2 containers, and each of those containers contains n moles of an ideal gas. We've got Na over here, Nb over here. I labeled them X and Y, even though they're called A and B there. Sorry about that. Both of those compartments are at the same initial pressure. Right? We say they're at the same initial pressure, same temperature, different numbers of moles and different volumes. But you pull the barrier out, and now the entire volume of that box is the combined volume of the 2 boxes that initially held those molecules. The total number of moles is Na plus Nb. The pressure doesn't change because the pressures were equal in these two boxes before you started. Removing the barrier doesn't change the pressure. Also, the pressure changes, or the total pressure stays at the value that was in each individual compartment. But what you're going to notice is that the Gibbs free energy of these species do change. What it shows that the Gibbs free energies do change. So, you look at Dalton's law of partial pressures. You might have to go back in your text and take another look at that, maybe you won't. But Dalton's law of partial pressures tells you that the pressure of each component of an ideal gas in a mixture is the mole fraction of that component times the total pressure, right? And so, in this situation here, the partial pressure of A is the mole fraction of A times that total P. And the partial pressure of B is the mole fraction of B times that, that total initial pressure, right? Initial pressure, the total pressure in the box. And so what we want to do now is we want to use the pressures of those components to relate their Gibbs free energies. And we're going to set up an equation that says delta G is G final minus G initial. Right now we're just looking at the final free energies of those components. So if we look at component A, we said that the chemical potential is the standard chemical potential plus RT times the natural log of the pressure. Well, now our pressure takes this form, mole fraction times total pressure, and the total Gibbs free energy of A molecules is the number of A molecules times their molar Gibbs free energy. So we multiply A times that term that we had for the chemical potential. We add to that the chemical potentials of B molecules, and the B molecules, again, it's chemical potential in the standard state plus that correction, that pressure-based correction. And again, the pressure is expressed as the mole fraction times the total pressure. And the initial Gibbs free energy was just the sums of the chemical, or the free energies of the gases. At that pressure that they started off at, in the absence of any mixing. And so we get this term Na times mu A plus RT line P for the chemical potentials of A molecules, and mu B, or Nb times mu B plus RT line P for the chemical potentials of B molecules. You'll notice that the Na mu A term here cancels with the Na mu A term here, right? And this little section, RT, natural log of XA times P, can be broken apart into two components. One is RT times the natural log of XA, and the other one is RT times the natural log of P, right? By the properties of logarithms, these can be separated out into two terms. And so there's an RT natural log of P term here that can cancel with the RT natural log of P term there. And similarly for the B, there's an RT line P term in the reactants that cancels with the RT log of P term that comes from this when you separate out the mole fraction and pressure terms. And so the only thing that we end up being left with after everything is said and done is these RT natural log of mole fraction terms. And so the total delta G for the mixing ends up being RT times number of molecules of A times natural log of the mole fraction of A plus number of molecules of B times the natural log of the mole fraction of B. Right? And that's our total value for delta G of that process. Is that delta G negative or positive? Shit. Should have thought before I asked that question. Okay. Since the mole fraction terms are less than 1, the natural log of anything that's less than 1 is negative. And so this term and this term have a negative sign in front of them. And so what we've shown is that the delta G for that process ends up being negative, right? And anytime you get a negative delta G, we know that the reaction is spontaneous, right? Positive delta G is non-spontaneous, negative delta G is spontaneous. And so because essentially because the partial pressures of those components drop when they mix, you end up with a reaction that has a favorable delta G, negative delta G.
So, you're just mixing some gases.
Just mixing some gases. And here's the follow-up to that. So it turns out that the expression that we derived, that I already got rid of, sorry, that the expression that had RT times the natural logs of the mole fractions, that expression is simply T times delta S. If I had given you in fact I did give you an example, or a problem early on where we said calculate the change in entropy when an ideal gas expands into a new volume. Do you guys remember that? We ended up having to take an isothermal reversible path because the temperature of an ideal gas won't change when it's expanding because there's no interactions between ideal gas molecules. Anyway, we've already done a calculation where we showed what delta S is for the expansion of an ideal gas. And it turns out that the delta G that we just calculated is simply T times the delta S that we would have calculated if we calculated the change in entropy for both of those systems as they expanded into the new volume. What that's telling you is that, what that's highlighting is that for these ideal systems, ideal gas systems, and we'll find ideal solution systems, mixing is entropy driven. So there's no change in H. H is the enthalpy, right? And the enthalpy is if interactions, if the magnitudes or strengths of the interactions change, then you'll have that electric potential energy that is released when you're entering or when you're leaving one type of chemical interaction and moving to another interaction, right? So if the forces that exist between two X gas species are different than the forces that exist between two Y species, then as they mix, there'll be a change in kind of the electric potential energies. If that had been the case, we wouldn't have had a delta H is equal to 0. We would have felt some heat come off because, or some heat be absorbed or some heat evolved because of the electric potential energy that changed in the reaction. In this case, in the case of ideal gases and ideal solutions, we kind of assume that the interactions here are identical in magnitude and type to the interactions here. And so when the two species end up mixing, there isn't a change in that electrical potential energy. And so you don't see heat being evolved or being absorbed in the reaction. So, but what does happen is there's an increase in entropy. And we can calculate that increase. We could have calculated that change in entropy two ways. Or we could have calculated delta G two ways. We could have calculated it the way we did, or we could have calculated delta S and then simply multiplied T by delta S, and we would have gotten the same delta G. Okay? So just as a reminder, mixing of ideal systems is spontaneous due to entropy effects. So we've got an expression that tells us how to calculate the delta G, or not the delta G, but the Gibbs free energy of gas phase species. And we want to be able to apply this to liquid phase species. And the key to being able to do this is to consider a liquid that's in equilibrium with its vapor. So we talked about vapor pressure, right? We said that every chemical species has a characteristic pressure that the gas will have above a body of the liquid if you're in a closed system, right? So if you're in a closed system, that liquid is going to evaporate until it achieves some pressure that's the vapor pressure. And once it's at the vapor pressure, the rate at which gas phase molecules collide with this surface and capture will be equal to the rate at which liquid molecules escape that liquid state and move into the gas state. So when we're at the vapor pressure, when we're at key vaporization, we have equilibrium between the gas and the liquid phases, right? What are the relative chemical potentials of the gas phase species and the liquid phase species if we're at equilibrium? They're equal. They're identical. If you're at equilibrium, if you're, okay, so delta G, we've learned is a measure to determine whether or not a reaction will happen spontaneously or not, right? If delta G is 0, there's no net driving force behind the reaction. If the delta G is non-zero, there'll be a net driving force for the reaction in one direction or another. At equilibrium, delta G is 0. And so that means if delta G is, say if we're going from the liquid to the gas phase, would be G of the liquid minus G of the gas, right? The products, the reactants. Then for delta G to be 0, these two have to be identical. Yeah? And so we know that if we've got an equilibrium between a liquid and the vapor, that we have a situation where delta G is 0, therefore the chemical potentials of each species are identical. And so that's a really easy way to measure the G of the liquid. We just measure the vapor pressure of the gas, and we say that now we say that the mu of the liquid is equal to mu of the gas. Mu of the gas is mu naught plus RT line P, where mu naught is the chemical potential at the standard pressure, right? So we have that plus the RT line P term, and you can just cross out the gas here and put liquid, and say that that's also the chemical potential of the liquid. Yeah? I put people to sleep. Maybe it's all the partying from the 49ers game. You guys all stoked that the 49ers won? So when you have that equilibrium condition, you can say that the chemical potentials of two species are identical, right? So chemical potential of the liquid, chemical potential of the gas, absolutely identical. You can express the chemical potential of the gas in terms of its standard chemical potential at 1 atmosphere plus the correction term, and that's that correction term that we derived, RT times the natural log of P, where the P would be, the P now would be the pressure of the vapor, yeah? The vapor pressure of that system. And so this expression, again, because liquid and gas are equal, this expression is also equal to the chemical potential of the liquid under equilibrium conditions. So now we've got an expression for the chemical potential of the liquid. And we're going to use that.
I have a question.
Yeah.
Is this going to be an exam, chapter 6?
Yeah. We're gonna do a study session on Tuesday, and so you'll have some homework problems. You go. I gotta write them up, but you go home tonight and you look on Eiler, and there'll be a new homework set for all this material. You take a look at it over the weekend, and we'll come back here on Tuesday and we'll work a bunch of problems. Yeah, I'll give you answers too. We'll come back here on Tuesday, we'll work through problems, and then hopefully by Thursday we'll be ready to take an exam on this.
We should make a take-home exam.
You might get a take-home exam.
That would be nice. Very easy.
We should vote. Take-home exam.
I waited until the last exam to have a take-home exam. I might do that again, let you guys have the last one as a take-home. Okay. So now we're going to consider the chemical potential of a species in solution with another component, right? And we'll go back for a second to that image that was previously there where we had equilibrium between the liquid and the gas states, and we said the chemical potential of the liquid is going to be equal to the chemical potential of the gas. The top of that surface of the liquid looked something like this. The entire surface was covered with solvent molecules, right? When we make a solution, you can kind of think of that surface as changing because now in some places where we used to have occupation by solid molecules, we now have solute molecules. What that does is it decreases the effective surface area that the solvent has available to it for leaving the liquid phase and going into the gas phase, right? There's simply not as much surface area over here for solvent molecules as there was here. And so you might be able to imagine that because the amount of space occupied by the solvent molecules decreases, that it wouldn't be as able to drive molecules into the gas phase as it would be in the pure solution. And it turns out that this is experimentally verifiable when you have a solute dissolved into a solvent, the vapor pressure of the solute drops. What do you guys, if the vapor pressure drops, what's happening to the Gibbs free energy? Huh?
The pressure drops.
Goes down. Remember we said that we have that equation up there. It's sitting right here. The chemical potential is the standard chemical potential plus RT times the natural log of P, but that P is P divided by the standard pressure at 1 bar, right? If that P goes down relative to where it was at previously, then that's going to be a lowering of the chemical potential. If that P increases relative to where it was at initially or previously, then the chemical potential is increasing. And so, in the situation where we have solvent or solute dissolved in solvent, we see that the vapor pressure of the solvent goes down, and we can intuit then that that means that the chemical potential of the solvent dropped. If its vapor pressure drops, its chemical potential drops. And so we have the result that that the addition of a solute lowers the chemical potential of the solvent. And assuming that these are ideal solutions, so we'll talk a little bit more about ideal solutions. Assuming that they're ideal solutions, the same exact relationship holds for the solute. The solute chemical potential will drop when it goes into the solution as well. So, yes, let's finish this thought real quick here. Raoult's law applies only to ideal solutions, and ideal solutions are the type that we were talking about when I talk about the mixing of those gases. I know that's not liquid phase, it's gas phase, but it applies also to liquid phase. In these liquid solutions, if the solvent-solute interactions and the solvent-solvent interactions are roughly equivalent, then the if solute-solute and solvent-solvent interactions are roughly equivalent, then the solvent-solute interactions will also be equivalent. And in that case, you get the relationship that Raoult came to, which is equation 6.10, that the pressure of the gas in solution is equal to pressure in the pure liquid. So this PJ star, that means the pressure of the pure